Okay, so earlier we got our exponential model. So the next thing that I'm going to do is I'm going to take the derivative of our exponential model, which is going to tell me the speed of increase or decrease. So the speed of the growth of the channel, and that's going to give me a unit that will be amount of subscribers per, now our unit is going to be time here, so per month. So that is what the derivative is going to tell us. At any given point in this year of time frame that we've got graphed, what is the amount of subs per month? So again, to do that, I'm going to do dy over dt is equal to d over dt, bracket 80 e to the power of 1 over 5 ln 5 over 8 t plus 5430. Now, an important thing to do up here as well, once you've got that, let's just make sure that we graphed it. This is a different day from yesterday. Yeah, so we graphed it yesterday, so good. Okay, so next thing we're going to do, sorry, this should be in the bracket around here, not over there. Okay, so when I take the derivative of this part, it's just going to become 0. It's got no t's to give us. When I take the derivative of my exponential function, I'm going to derive this top section here. Now, all of this stuff at the front is just a number. If I put it into my graphics calculator, okay, so if I put it into my graphics calculator, you'll see it's going to give me a number. So it's just going to be like whatever that decimal is, and then the derivative of that. So, well, so there you go. That number here is like negative 0.094 blah, 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 blah. Now, we don't want to use that one. We want to keep it in exact form so that we're not getting all of that rounding error at the end. Anytime that you round something, especially with an exponential function, you'll have rounding errors. And because they're exponential or logarithmic functions, those errors can compound very quickly and make your data unreliable. So it's going to be 80 times this part here, 1 over 5 ln 5 over 8 e to the power of all of that again. T, and that's going to give me dy over dt. Now the 80 can be cancelled out with the 5. So if I do 80 divided by 5, or I could have done that in my head, it's going to be 16. So 16 ln 5 over 8 e over 5 ln 5 over 8 t. Now, while we're here, we're going to do our second derivative as well. So that is the first derivative. If I input a time for the month, so if I input 3, that will tell me in the third month what is the amount of subscribers that were subscribing per month. Okay, now second derivative is going to tell us the acceleration of the growth. So now we're going to be taking the double derivative here. So that's why here, if you think about what would be getting put over here, that is getting put there again, which is why the d is squared and the dt at the bottom is squared. It's going to be equal to d over dt for this function here above, 16 ln 5 over 8 e to the power of 1 over 5 ln 5 over 8 t. Now, when we take the derivative of this, the same thing is going to be coming down. So it's going to become 16 times 1 over 5 ln 5 over 8 times ln 5 over 8. If you're wondering what just happened, I didn't mean to, but for some reason, when I derived it, I put this part in here in between these two. So you don't have to do it that way, but they're all multiplying, so you're going to get the same answer anyway. T, okay, so that will be our second derivative for the acceleration of growth. So what does acceleration show you? It's going to show you what the function of the speed of the growth is with respect to the months. Okay, so now if I simplify what I've got here, I'm going to end up with 16 over 5. We can't simplify that. ln 5 over 8 squared e to the power of 1 over 5 ln 5 over 8 t, and that is our second derivative. Now, obviously, I would type this all up nicely in my Excel document, but our next step is going to be to fill in this part here. Now, these values are the same for everything. This part here represents your initial data. Now, the next thing we're going to do is press equals. And now so at this point, it's going to look like I've done some magic because I've had to edit the video to chop some things out just while I got my code to work. So over here in my exponential graph, or my exponential function table, if I click this cell here, this is the code that I've entered in to say that I'm doing this here. Now, this blue part here is referring back over into my table of values so that I can get all of the different speeds that are occurring at that point. So you can see here that my fastest speed is at the initial because of the way that I've done this graph. So you could say that it is decelerating. I'm losing the most amount of subscribers at the start, and then it starts to taper off. So we're still losing subscribers down here, but that rate of loss is less. Now, the other conclusion that we can draw here, if I click there, you can see that's the code that I've used to input this function. So all you'll need to do is adjust it for your function. So the conclusion I can draw here, because all of these accelerations are positive, it is gaining speed at losing subscribers. So because the acceleration is positive, that's what the conclusion that we can draw there.